Okay. Now I may discuss on another approach, which is we need to use graphical methods. Okay, based on Kuhlman. Okay, the previous one we use hand calculations. Okay, so but for this case, we may use a Kuhlman methods. Okay, and uh, for me, we need to do a comparison later on if you want to if anybody asks which one is much more better. Okay, so for me we need to do a comparison later on. Okay, so for example, Coleman developed a graphical method for determination of the active force PA developed behind a retaining wall. Okay, so then Kapila has improvised the method by Kuhlman. Okay. So and then Kapila has explained a little bit on the polygon force, which is what been discussed previously by uh, Okabe. Okay. So he has introduced what we call as the W, okay, square root of 1 minus kV square plus kh square. Okay. So sorry. Okay, so this is example from what we have discussed previously. Okay, from the polygon force. Uh, okay, note that in figure 8.9a, okay, P and alpha is the angle that the failure which makes with the horizontal. Okay. So the idea behind this graphical construction is to determine the maximum value of PAE by considering several trial waves with reference to figure 8.9c, okay, where the following step for the graphical constructions are listed in the next slide. Okay, so this is how they come up with the derivation. Okay, based on the 8.2, which is we have discussed previously on the Okabe. Okay, so then he has improvised the one that has been produced by Okabe, okay, by including the W square root 1 minus kV square plus kh. Okay. Then okay, this is what the procedure, okay, to solve the problems by using the graphical constructions, okay, which is we may discuss later on. Okay. So okay. So for example, if we have a problems, so either we want to solve by using the hand calculations, or we can use this uh, graphical uh, approach. Okay. However, we need to draw in a very good scale. Okay. So in this case, it is better for us to use the grid paper or the or what we call as a graph paper. Okay, because we need to get the exactly scale. Okay. Okay. So the step here. Okay. So we need to use the same theta. Okay. Formula. Okay, which is the theta from the previous discussions. Okay, so this is the value of the theta. Okay, so we may use the same theta equation. So first, calculate first the phi minus theta. Okay, okay. So to begin with, first we need to construct. We need to choose any datums. Okay. So then we need to construct what would be the heights of the retaining structure. Okay. For example, this is the height. Okay. So we need to construct the actual heights. Okay. But we need to make sure that we use the consistent scale. Okay. Then from there we may construct for example for the retaining slopes. Okay. And also the backface slopes. Okay. So that is our first task. Okay. Then our reference is what we call as the horizontal line. Okay. Got as the x-axis. Okay. So first calculate the phi minus theta. Okay. Then by using okay, another thing we need to bring along our protector. Protector. The protector. Okay. Because we need to use the actual value. Okay. For example, if this is 42, okay. So we need to refer to the protector, okay, and draw a line, okay, to represent BE. Okay. So the next step is to calculate what will be the value of 90 degree minus beta minus delta, which is the friction angle, the friction of the wall and soil, and minus theta. Okay. So that will be the next step. Okay. So then by using the same protector, okay, so by referring to the BE, so we may extend uh, the degree, okay, and draw the BD. Okay, so this is the first step, or this is second step. Okay, so that is the BD. Okay. Then, okay, so we may draw what we call as trial failure surface. Okay? So for this case, the trial failure surface is B to C1, B, C2, B, C3, and B, C4. Okay. So this is the third step. Okay. So what we call it, how to draw it. Okay. For example, you may use a consistent length. Okay. For example, if this yeah if this you decide as 3, okay, so you may use 3, 3, and 3 interval, for example. Okay, so that is the third step. Okay, and later on, your KH and KV, KH and KV. Okay, so I guess you can get from what we call as from the actual calculation, from the input that we provided. Okay, which is the KH and KV. Okay. Okay, so this will be the step number 4. Okay, sorry, I need to refer to the procedure. Okay, so later on, you need to determine what will be the value of this trial failure. Okay, so how to get it? Okay, so you need to use what we call as the area for the triangle. Okay, which is half times the length and the width. Okay. But if it's in perfect triangle, so there will be no problem. But if not a perfect triangle, so you need to get the equations. Okay, perfect means that it is a 90. They have a 90-degree. Okay, so you need to determine what will be the width for each failure trial failure. Okay, so that is for the W. Okay, once we have obtained the W, so you need to multiply with the one that this one, okay, with this formula, okay, from the KV. Okay, so from there, that is your W1 prime, W2 prime, and so on and so forth. Okay, so that is the step number 6. Okay, and the step number 7. Okay, so okay, you need to come up with your own scale. Okay, for example, 1 centimeter equal to whatever value that you want to choose. Okay, for example, 500 500 kilonewton per meter run. Okay, so that is your scale. Okay, so you may use whatever scale that you are feel comfortable to be used. Okay, okay, so now you know what is the value of your W1 prime. Okay, W2 prime. Okay, so you need to draw all this value. Okay, on the line of BE. Okay, for example, if the value is equal to 500 here. Okay, so you use a ruler. Okay, which is represent 1 centimeter. Okay, then continue for the F2. Okay, from here to F2, what will be the value? Okay, so then you have F1, F2, F3, and F4. Okay, so that is the value of your what we call as of your width of your W. Okay, okay, so that is for the F1, F2, F3, and F4. Okay, so the procedure of number 5. Okay, you may draw a tangent. Okay, from the F towards the line of BC1, for example. Okay, and also the same towards for F2 towards the line of BC2. Okay, and number 3, F3 towards the line of BC3. Okay, so that is the next step. Okay, okay, so once you have draw the line until it meets the BC. Okay, in a tangent value, in the tangent sorry, okay, sorry, not a tangent. Okay, so now you have a F1. Okay, so you need to refer the BD. Okay, this is the BD. Okay, it should be tangent to the BD. Okay, for example, if the F1, okay, this is the F1, so this line should be tangent with the BD until it meet the C1. Okay, I repeat again. Okay, uh, to get the point of G1, okay, so your F1 should be parallel to the BD line. Okay, so this is the BD line. Okay, so from there, the intersection of the line of F1, okay, with the BC is the G. Okay, so the same goes to the other line. Okay, so this is the F2, F3, and F4. Okay, so it should be parallel with the line of BD. Okay, so all these points should be connected smoothly. Okay, so you need to have what we call as a curve ruler. Okay, the ruler that could be bent. Okay, so you need to have a, a ruler that could be bent. Okay, and then you combine all the line. Okay, in a very smooth curve. Okay, so that is the step number 10. Okay, then the step number 11. Okay, draw a tangent line. Okay, which is towards the what we call as the G, towards the curve. Okay, so this will become the HG. Okay, so tangent line should be 90 degree towards the curve. Okay, okay, so the point of the point of the tangent. Okay, uh okay, the point of the tangent. Okay, then you may refer to the BD as well. Okay, to draw a line which is parallel to BD. Okay, until it meet the BE. Okay, so this is the F value. Okay, so your F, which is obtained here, okay, multiply with the scale that you has been used, okay, to get the value for the PAE. Okay, so that is the Kuhlman methods. Okay, I repeat again, from from the start. Okay, so the first procedure. Okay, I will try to discard this because okay, okay. First you need to determine the theta value. Okay, so the theta you may obtain from the previous equation. Okay, so then you may draw a line. Okay, which is the BE. Okay, so this is the BE line, where the BE is equal to theta minus phi minus theta. Okay, so that is the first line that you may create. Okay, so the second line is the BD line. Okay, this is the BD line. So how to create the BD line? 90 minus beta minus delta minus theta. Okay, so that is for the BD. Okay, the third step, you may construct a trial failure surface. Okay, on the top of the slope. Okay, for example here. Okay, with approximately a same interval of distance. Okay. For example, A to C1, okay, 3 meter. C1 to C2, 3 centimeter, for example. C2 to C2 to C3, 3 centimeter. C3 to C4, 3 centimeter. Okay. So that is the step number 3 in terms of to construct a line. Okay. Okay. Then step number 4, get the value of the KH and KV. Okay. And later on, get the value of the sigma square root. So I need to refer to the notes. Okay. Square root 1 minus KH, 1 minus KV square plus KH square. Okay. So that is step number 4. Okay. So then step number 5, we need to count for the wedge area for the trial surface. Okay. So W1, W2, W4. Okay. Then multiply with W1 with these equations. Okay. W1 multiply with this square root 1 minus KV square times KH square. Okay. So that is for W1, W2, W3, W4. Okay. Then the next step, okay, is to use or to adopt a load scale. Okay. For example, because for example, if you want to use 1 centimeter equal to 500 kilonewton per meter square, 1 kilonewton per meter. Okay. So you may draw it on the BE line. Okay. For example, B to F1. Okay. Refer to the width of the W. Okay. Times the square root 1 minus KV square plus KH square. Okay. So then the next is from F1 to F2, another load represent the W2 times the coefficients of that, the coefficient of KV and KV. Okay. And then repeat with F3 and F4. Okay. So the next step is to construct for the G1, okay, G1, G2, and G3 and G4. Okay. So we may refer to the BD. Okay. So the line should be parallel with the BD. Okay. So the point which is meet the CBC line is the G1. The point that meet with the BC2 is the G2. The point that meet with the BC3 is the G4. And the point that meet with the BC4 is the G4. Okay. Later on, you may combine all the line. Okay. So it is suggested to use a bending ruler. Okay. A flexible ruler. Okay. So then determine a tangent line. Okay. Which is represent the HJ here. HJ. Okay. So the point that represent the intersection, the intersection between the G curve with the tangent line is the G. Okay. Then by refer to the BD, we draw a line which is parallel until it meet the BE. Okay. So the F is the value for the force which is represent the PAE. Okay. So how to get the value? So we need to use the scale. So what is the distance between B to F based on the scale? So we multiply the scaling value, the scaling factor value. Then we may get what we call as the value for the PAE. Okay. So that is the way how we use the Coleman approach. Okay. Okay. So now I will move to another chapter. I will discuss on the Bracecut first. Okay. Okay. I may discuss on the Bracecut design. Okay. However, for the Bracecut design, it's not related to the what we call as to the dynamic approach. Okay. Um, okay, because we have discussed on what we call it on the lateral earth pressure. Okay. So it would be wise for us to discuss on the Bracecut. Okay. Okay. So for the Bracecut design, okay. Um, okay. Let me introduce first what is the Bracecut. Okay. So deep excavation with vertical side require lateral supports to prevent cave-in of the earth and to protect the adjacent area against ground subsidence and lateral movement of the soil. Okay. So is that, for example, if we want to construct a basement, for example, okay, uh, if the height or the basement is very deep, okay, so we need to have a something or some structure to restrain from the soil to move inside. Okay. At the same time, it can protect, okay, from any movement or deformations, okay, or failure of the trench area. So when excavation are shallow and ample space is available, the site of the excavation can be sloped at a safe angle to ensure stability. Okay. For example, if the height of the hole or the depth of the trench is not is not too high, so we can easily construct a slope, okay, to protect, okay, the failure. Okay. However, in deep excavation, especially in built up area, there may not be adequate space for providing slope. Okay. So if the area is too high, so if the excavation is too deep, so it's not suggested to have a slope. Okay, because we need to have what we call as a large area. Okay, to 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 construct a slope, because the slope should be 27 degree. Okay, to make sure it is safe to be constructed. Moreover, it becomes uneconomical to provide safe slope because of large quantity of earth involved. Okay? So at the end, we need, if you, for example, if you construct slope, so we need to excavate this area and to do the cutting, there will be another cost, and to bring it away, so they will, or throw it away, there will be another cost. Okay, so the best solution is to have to design for a brace cut. Okay, so excavation which are laterally supported are braced. Okay, So this is example of the Bracecut design in the figure. Okay, shown in the figure. Okay, so the vertical side of excavation are supported by a sheeting and a bracing system. Okay, so this is a sheet, or we call it as a we can use a sheet pile or whatever pile, timber pile also can be used. Okay, it consists of relatively flexible sheeting placed against excavation wall. Okay, the lateral thrust on the sheeting is resisted by the horizontal member in compression. Okay, so then they have a strut. Okay, they call this is a strut members. Okay, and in the strut, okay, this is on the what we call on the uh, side view. Okay, on the front view, sorry, front view. Okay, when we look on the side view, okay, uh, the we call as a they are a wheel, okay, which is put on the strut. Bracing is provided as excavation proceeds and the face of sheeting becomes exposed. So various type of bracing system is adopted to make the excavation stable. Okay, so there will be a lot of methods, a lot of what we call as uh, approach or material can be used. Okay, sheet piling is used primarily as a bulkhead to hold or restrict the lateral movement behind it. Okay, so for example is a sheet pile. Okay, normally being used. Okay. So what we call as this brace cut is not a permanent structure. Okay, it's a temporary. Okay, so for example, if you want to have a what we call as a permanent structure, so we can use the gravity retaining wall. Okay, from what we have discussed on the previous chapter. Okay, but when excavation is temporary, excavation for building a subway, the excavation is filled with structure which then permanently retain surrounding soil earth. If the temporary excavation is made on the sand, the wall of the excavation must be supported during construction of the building by using a system of bracing. Okay, so this is example of constructions, okay, which is laying underground pipeline, construction of bridge abutment, construction of basement, metro railway construction of subway tunnel. Okay, so this is example of the Bracecut system has been used. Okay, type of the Bracecut system, we have here vertical timber sheeting, uh, steel sheet pile, soldier beams, and tie backs. Okay, so this is example of the system that been used. Okay, so for example, for this vertical timber sheeting, in this method, vertical timber sheeting consisting of planks about 8 to 10 centimeter thick are driven around the boundary of the proposed excavation to the depth below the base of the excavation. Okay, the soil between the sheeting is excavated. The sheeting is held in place by a system of walls and struts. Okay, wheels and strut. The wheels are the horizontal beam running parallel to the excavation wall. The wheels are supported by the horizontal strut which extend from the side of the excavation. Okay, so means that this is the sheet pile. Okay, so there will be a wheel and the strut will be like this. Strut. Okay. So the sheet part is the main bracing system. Okay, and in addition, they have a wheel. Okay, running parallel to the excavation. Okay, and also the strut. Okay. However, if the excavation are identified and you can economically support the wheel by inclined strut, okay, known as rakers. Okay, so there will be another system they call as rakers. Okay. For inclined strut to be successful, installation in the soil in the base of the excavation is strong enough to provide the quick reaction. Okay. So this is example of the system. Okay. If the soil can temporarily support itself and an excavation of limited depth without an external support, the timber sheeting can be installed in the open or in partially complete excavation. Vertical timber sheeting economical up to depth of 4 to 6 meters. Okay, so it's been suggested if we want to use the timber sheeting methods, so we can go up to 4 or to 6 meter height. Okay. For steel sheet pile, okay, pile or sheeting driven in close contact to form a continuous interlocking wall which resists the lateral pressure of the earth of water of earth. In this method, the sheet pile is driven around the boundary of the proposed excavation. Okay. The continuous line of the line is driven in advance of excavation as the soil is excavated from the exclusion weights and strut are placed. Okay. So the wheel are made of the steel. The lateral thrust from the side is resisted by horizontal member or strut are placed across the excavation and which again the wheel. The strut may be of the steel or woods. Okay. I guess the same, but the difference is in terms of the material with the timber. Okay. So as the excavation process, another set of wheel and strut is insert. Okay. So this is to construct in stages mode. The process is continued until the excavation is complete. It's recommended the sheet pile should be driven several meters below the bottom excavation to prevent local heaps. If the width of the excavation is large, inclined bracing may be used. The upper strut is placed when the excavation is shallow and the little lateral yield of soil has occurs to change applicable appreciably the original state of stress. As excavation proceeds downward, the lower part of the face is freely to yield inward before it can be restrained by next strut. The inward yield of soil increase with the increase of the depth of excavation. Those problem is analogs to a retaining wall tilting about 8 tips, the sheeting tips about 8 tops. Okay. So this is an example, okay, where we normally we may construct in what we call it in stages. Okay. Okay, so this is the, the sheet pile on the plan view. Okay. So this is the sheet pile, this is the wheel, okay, and this is the strut. So this will continue till the end of the excavation length. Okay. So this is example of the what we call of the team sheet pile. Okay. Continue sheet pile. Okay, this is another method soldier beams. Okay, by using the H pile. Okay, so previously they're using the sheet pile, so this is the H pile. I guess it has almost the same with the sheet pile. Okay. So in this case, the wedge play the most important rules. Okay. So another one is the tie back. Okay. If they doesn't want to use a bracing, so they use a tie back system. Okay. Especially if they want to have what we call as if there are no area to protect to install what we call as the bracing system. Okay. So to have a bracing, so then we need to have another. We need to have area to install the strut. Okay. So now we may look on how to do the calculations. Okay. To design for the Bracecut. Okay, definitely we need to use the Rankine column of pressure uh, approach, which is to get the Ka value. Okay, but the rest is not similar from what we use in the Rankine. Okay, the sheeting and the bracing system is somewhat flexible, and rotation takes place at the top of the wall. Sheeting are placed against the wall of the excavation when these are shallow. The upper strut is placed when the excavation is shallow in the lateral yield of the soil has occurred. As the excavation proceeds downward, the lower part of the face is free yield inward between the next strut is placed. Okay. So they're using a pressure distributions methods, okay, where we may differentiate between what we call as sand and clay, okay, because what we call as the pressure distribution is different, okay. Uh, so for example, if you want to uh, for sand material, okay, so we have a different what we call it as pressure distributions, okay, and we may refer to the what we call as to the Rankine Ka, okay, to to do the calculations, okay, okay, and this is the the pressure distribution diagram, okay, which is depends on the type of the material, okay, where we have sand, and the distribution diagram or distribution pressure is 0.65 times unit width time H and time Ka. Okay. While for the clay, we have two types of distribution diagram. Okay. So for example, if the clay is firm, so we may use the distribution diagram as shown in the B. If the clay is soft to medium clay, so we may use the distribution diagram as shown in the C. Okay. In order to determine either the clay is firm or soft, so we may use the stability number here, okay, which is gamma H over C. Okay. So if gamma H over C is less than 4, so we may use the distribution diagram of number 4. Okay. So if the distribution diagram, if the gamma H over C is greater than 4, so we may use the distribution diagram of C. Okay. So I will discuss first on the sand. Okay. And then I will provide to you the example for the clay. Okay. So we try to solve the example for the sand first. Okay. And then I will share with you for the clay, okay, which is not discussed in the lecture, but I will share with you how to uh, measure or to design based on the clay. Okay. So for the sand, okay, uh, this is all the information for the soil properties. Okay. So this is the diagram. This is the what we call as the, uh, the side view of the the front view of the bracing system. Okay. So before we begin, we need to look on the distribution diagrams here. Okay, because it is represent the sand, so we may use the A distribution diagram, which is to get the pressure represent the sand, so we may use 0.65 times unit weight times H times Ka. Okay, so 0.65 times H times unit weight times Ka. Okay, so that is the formula that we use. Okay, so definitely if definitely the C will be 0 because it's sand. Okay, so Ka should be calculate first. Okay, so to calculate the Ka, we may use this formula. Okay, it's from the Rankine approach. This is not from the column. Okay, this is from Rankine. Okay, so then calculate for the PA. Okay, so the PA is equal to 23. Okay, 0.65 times 18.5 times 8 tangent square 45 minus 38 over 2. Okay, so that is for the PA. Okay, then this is the distribution diagrams. Okay, in order to know what will be the stress, so we need to construct for the moment diagrams. Okay, so it's similar with the with what we design, for example, for the beam. Okay, so we need to know what will be the shear stress diagram and also the moment diagram. Okay, so okay, we have here RA, for example, and then we have here RB. Okay, so okay, in this case, okay, due to the distance is similar, okay, means that from ground to A 1 meter, okay, from A to B 3 meter, from B to C 3 meter, from C to the base is 1 meter. So it's better for us to what we call as to separate into uh, two portions. Okay, so if we solve on the is one side, so means that we already solve for the second side. Okay, so this will be the RE and RB. Okay, so the distance of this will be distance 1 meter. This is 3 meter. Okay, so this is the reference. Okay, so we may determine what will be the RA and RB1. Okay, so RA will be represented as a RC later on. RB should be RB is equal to RB1 plus RB2. Okay, so by using the concept of moment, so we may solve the problems. Okay, by refer to the B. Okay, so for example, if to get the RA, okay, times 3, which is the distance between RA to B. Okay, based on the equilibrium approach. Okay, so this is 23 uniform distributed. Okay, so 23 times 4. Okay, that is the loads distribution load, and then need to multiply with the moment arm. It should be 2. Okay, So the result is equal to 61.33. Okay. So that is for the RA. Okay. Then for the RB, okay, is 23 times 4 minus with 60.33, so equal to 30.67. Okay, so that is for the R, what we call as RB. Okay, so RB1, RB2 is equal to 30.67. Okay, so and then RA is equal to RC. Okay, so to get the strut loads, okay, it's been provided here. The distance of the strut is 4 meter center to center. Okay, so then we may multiply, okay, what we call as the reaction from the RA with 4, then we get 245. Okay, then the value for the B is combination of RB1 and RB2, then multiply with the length of the strut. The distance of the strut is equal to 4. So the same value obtained in strut B and also strut C. Okay, so that is the value of the strut loads. Okay, then the maximum bending moment for the pile wall sections. Okay, so that to determine the maximum bending moment for the pile wall sections. Okay, consider the section DB and DB1 and B2E of the wall. Okay, from this shear force diagram. Okay, DB1, okay, B2E, okay. So we may calculate what will be the area for example, for this part, okay, and also for all parts. Okay, determine what will be the maximum bend, maximum moments. Okay, for example, for the M1, okay, the area is half times 1 times 23. Okay, for the MA and MC. Okay, and then for the MM, okay, uh, which is 30.67, okay, times 1.33 times half, so we gain 20.4. Okay, so in this case we may choose uh, the most the most higher value, okay, in order to design for the sheet pile. Okay, okay, for this case we only choose the positive side. Okay, okay, how to get the distance of 1.33 and 1.67? So we may use the similar triangle concept, okay, which is 38.33, okay, for example, y minus 3, okay, and 30.67 y. Okay, so from there we can get y, okay, which is equivalent to 1.33. Okay. The last one is to determine the maximum moment for wheels. Okay? The bending moment for wheel is referred to this equation. Okay? R L square over 8. Okay? So with the R is equal to maximum strut load 245, L is equal to the spacing of the strut 4 meter. So the maximum bending moment to design for the wheel is equal to 490 kilonewton meter. Okay? So then we need to choose or use a catalog, okay, to be referred to get the type of the material or the size of the structure or the material to be used, okay, by referring to all these informations, okay, or the size of the material. Okay, okay, so that's is for the Bracecut system. Okay, we take a rest and then we will continue at 11:45.